All right. Good afternoon, I guess. I don't know what time it is where you are. Not a genius. Can't read your mind. So here we go. We are going to learn about the work and kinetic energy theorem. It's going to be sweet. You ready? Here we go. So one of the things that we focused on last chapter in particular was this idea that if no work was done by non-conservative forces, a lot of negatives in there, or equivalently, if work is only done by conservative forces, then your object's total energy, i.e. the mechanical energy, is going to stay constant, all right? And I think I've said this before, but I should reiterate that technically I should be saying mechanical energy, because total energy would also include other forms of energy, like thermal energy, for example, which will come up at the end of this video, okay? So as long as the only forces doing work are conservative, your total energy, your mechanical energy, will stay the same. Which then begs the question, well, what if there are non-conservative forces doing work? Well, it stands to reason then that your total energy will change. Okay? And so how does that work? Well, we'll get to dealing with total energy in the next video. Here we're going to take a slightly different tack. All right, so what we're going to do is we're going to look at our net work. Okay? So again, sometimes I'm going to call it net work. I need to do better about making my W's look like W's. And sometimes I'll write it as net work. Okay, so you should be familiar using either notation. All right, well, so assuming that our net force is constant, then we ought to be able to say this. Our net work should be done by our net force as our object travels through some displacement, right? Okay, and assuming that everything is on one line, we can just multiply those two vectors, right? Okay, but check it out. We know, because of Newton's second law, that net force is just mass times acceleration. Oops. All right. Now, notice we also know from kinematics that 2 times acceleration times displacement is Vf squared minus Vi squared. Okay? So if I divide both sides by 2, I find that A delta R is 1/2 Vf squared minus 1/2 Vi squared, right? And so now what I can do is I can take this and substitute it with this. So my net work then, up here, my net work is going to become, well, let's see, I'm going to replace A delta R with this. So here's what we get. So this mess, we're going to get net work is, oh my gosh, my W's are terrible. My net work is mass times this. Oh my gosh, I wonder if you see what I see. Let's distribute that M. So our net work is now, oh my gosh, my W's, is now 1/2 mVf squared minus 1/2 mVi squared. That's final kinetic energy minus initial kinetic energy, which is change in kinetic energy. What? That's amazing. That is the work energy theorem. It's the work kinetic energy theorem. All right, and the work kinetic energy theorem simply says that the net work done on an object results in a change in kinetic energy. All right, conceptually, the way I always think about this is that net work is done by a net force, right? Net force results in acceleration, which results in a change in velocity, which results in a change in kinetic energy. Okay? So that is the work kinetic energy theorem. All right, that is basically going to be the premise behind this next worksheet that you guys are going to do to get some practice with this. All right, so let's do a couple quick examples here. So let's see if we can apply this. All right. So what we've got here is a 5-kilogram ball that's sitting at rest on a floor. Roy is going to exert an upwards constant force of 60 newtons on the ball before releasing it 2.5 meters above the floor. Find the velocity of the ball as he releases it. So this is one of those barrel throw problems that we did all the time in honors. All right, so here's the deal. We know that the initial velocity is 0. That means the kinetic energy is going to begin at 0. We know that it is a 5-kilogram ball, so we can certainly find our gravitational force. It's going to be negative 49 newtons. And then there's this upwards force from Roy, which is 60 newtons. And I think that's it, right? Because he's throwing it. So those are the only two forces. So it looks like our net force here is going to be, what, 11 newtons? Oh, well, then I can find my net work, right? Because that's just going to be my net force, which is constant, times my displacement, which happens to be vertical here. So I've got 11 newtons times 2.5 meters. It's going to give me 27.5 joules is my net work. But what the work kinetic energy theorem tells us is that that net work is also my change in kinetic energy. And remember, change in kinetic energy is final minus initial. All right? Please don't forget that definition of change, that it is final minus initial. So for us, our change is 27.5. We don't know our final kinetic energy. Our initial is 0. Aha! Our final kinetic energy must be 27.5 joules. And I happen to know that KE is 1/2 mv squared. So 27.5 is half of the mass of the ball times v squared. And solve for your velocity and you get 3.32 meters per second. Okay? Now, is that the easiest way to solve that problem? Absolutely not. But conceptually, what I want you guys to understand is that the net force here produced acceleration, right? Which results in a change in velocity, change in kinetic energy. Okay? All right, now obviously, as we go through the problems, they will get more complicated than that, but that's a good start. Okay? All right, now, let's talk about graphs, all right? Because everything that I've done here so far has been a constant force. But what happens if the force isn't constant? Well, remember, what we learned was that if your force is not constant, in this case our net force is not constant, you can calculate the net work by integrating your net force with respect to your position. Okay? So in this problem it says, consider the graph here. I'm going to begin this a little bit so you can see it a little better. Consider the graph here. It represents the net force, despite the fact that it's not labeled over here. This is supposed to be net force, acting on a 3-kilogram pixie as he runs along a telephone line. As the pixie travels through the origin, it has a velocity of 20 meters a second. Then A says, what is the maximum velocity achieved by the pixie? All right, well, notice my graph here is a net force versus position graph. All right, and remember, integral should lead you to think about area, right? So I can find the area under this curve, and that will tell me the net work done. All right. Oh, but remember, that net work is also my change in kinetic energy. All right, so let's take a minute. Let's zoom in here. And I'm going to just kind of break this up into triangles and rectangles, and we're going to find the areas. So this area here, let's see, it's 1/2 base times height. So my base is 10, my height is 60, 600, so half of that would be 300. So this guy here has an area of 300. All right, let's see, this little dude here is just a rectangle. So 5 times 600, that's also 300. Okay, let's see, this little chunk over here has a base of 15 and a height of 60. So that's going to give us an area of 450. Notice those are all positive areas. So this entire time, for all three of those little zones that I just dealt with, what is going on with my computer? For all of those little zones that I just found, we are gaining kinetic energy, right? So we have a positive force that's going to cause positive acceleration. It's going to cause an increase in velocity, okay? So we're going to be gaining energy. Now, this other part is negative. So if you find the area of, let's see, we haven't used purple yet. If you find the area of this dude, you end up getting negative 400, okay? So it looks like as soon as you pass 30 meters, as soon as my object gets past a position of 30 meters, I'm going to start losing kinetic energy because now the net work is negative. So here, when is the maximum velocity achieved? Well, that's going to occur when we have the most kinetic energy, which looks like it's going to happen at a position of 30, right? Because that's where we've sort of gained the most energy, right? And then after that, our change becomes negative. So in this part, we're going to now start losing energy. Okay? So, during this yellow chunk here, our total change in kinetic energy is 300 plus 300 plus 450 for a total gain of 1,050 joules. Well, what was our kinetic energy initially? It's half of the mass of the pixie times his velocity squared. So 20 squared is 400, times 1.5 is 600 joules. So we started with 600 joules, we gained 1,050. That means our final kinetic energy is going to be 1,650. And from that you can find your velocity, right? Just by rearranging your kinetic energy equation. Okay, that's the 1/2 mv squared equation, just rearranged. And it gives you 33.2 meters per second. So that's the maximum kinetic energy, right? Because then after that period, we start losing energy again. All right. Now, let's talk about this next part. Whoa. All right, so the next part, let me erase all this garbage. Oh, come on. There we go. All right. So question B says, at what position does the pixie's velocity, oh, I forgot my apostrophe there, grammar please. At what position does the pixie's velocity equal his, this is worded terribly, it's supposed to be a typo. Here's what I did a terrible job of writing the question of. What I was trying to ask you is this. When he gets here, he's going to have some velocity. At what other time does he have the same velocity? Okay. So what I know is here, he lost 400 joules, right? That was the area we found before. So if he lost 400 joules of kinetic energy there, then we got to figure out how far back do I have to go here to have positive 400 joules. Okay? And notice this whole triangle here, remember this whole triangle was positive 450. So in this chunk he gained 450, in this chunk he lost 400, so that's a net gain, right? So we need to figure out where do we have to go back here for this purple area to represent positive 400 joules. So that the 400 joules I gain here are canceled out by the 400 joules I lose over here. All right, so we got to do a little bit of algebra here. Let's call this little chunk here delta x. All right, now for this whole, we got to figure out, so if this is delta x, what's this height over here? So it turns out that this line here, I want to say this line here, let's see, well, so our rise is, this is 15 and this is 60, so it looks like 60 over 15, so our slope looks like it's -4, right? Okay, so if I go over, oh man, I'm doing a rotten job explaining this. So if this is delta x, then this has to be 4 delta x, right? Because the slope of that line there is 4, well, -4, but we're not worried about the signs, right? So, I guess the question then is, that's a triangle, so it's 1/2 base times height, and we want that to equal positive 400. So this is 2 delta x squared is 400. Solve this, and your delta x ends up being a number that I've written on this piece of paper over here, 14.1 meters. So what that means then is if this is a position of 30, and I go back 14.1 meters, looks like 15.9 meters is going to be my final answer there. Okay? That's a tricky one. because that area there is a triangle. That one was definitely challenging. All right, but I guess if I lost you there with the math, I guess the big thing that I want to make sure that you understand there is that these areas represent change in energy, right? So if we can kind of wrap our heads around the idea that during this chunk we lost 400 joules of energy, then if I can figure out, what chunk over here represents a gain of 400 joules, then that means that this position here and this position here will have the same energy, right? All right. I guess that is that. Oh my goodness. Oh, little pause button. It's like right there. Sometimes I'm not very smart.